Welcome to your lesson on functions as models. In this video, we'll look at how function notation is used to represent real-life situations. Let's take some notes on the notes packet that was provided to you. Beginning here. First of all, you should know that when you're creating and using functions, the independent variable is also known as the input, and dependent variable is known as the output. Here are some examples of relations. For example, there's a relationship between money made and shoes sold. So let's say somebody's selling shoes at a store. Which one is the independent variable? Or the dependent one? Well, the dependent one is money made, because the money you make depends on the number of shoes you sell. So the independent variable is S, shoes sold. In function notation, we can write that as M of S. That means money made based on the input of shoes sold. Let's try the next one like that. So hours spent studying and marks or grades earned. So what would be the function notation for that one? In this case, the marks depend on hours spent studying. So the marks you earn depend on hours. So marks depend on hours, which is independent, and the function notation then marks depend on hours. So the hours are the input, the marks you get are the output. Let's try the next one. Ozone layer depth and skin cancer cases. In this case, the function notation is S of O. The dependent variable is skin cancer cases, because the number of skin cancer cases there are depends on how deep the ozone layer is. So we have skin cancer cases dependent on the input of ozone layer depth. Finally, we have number of college courses completed and the salary a person makes. In this case, you could say salary depends on college courses completed. The more college courses you complete, higher your salary, perhaps. So dependent salary depends on college courses you've taken. That's an introduction to what's called function notation for real-life situations. We've looked at function notation as f of x or g of x, that kind of thing. But here you can see that the variables can very much represent the real-life thing that we are talking about. Okay, as an example, we have Chris makes money, a profit, from selling homemade hats. The profit he makes can be better expressed using functional notation. So here's the functional notation for his profit. Here's profit is the dependent variable, and it depends on the independent variable, which is hats sold. So profit based on hats sold. And here's our function. This means the profit he makes based on the number of hats he sells. Let's use that function to answer these questions. Number one, he sells 8 hats. Find the profit. We are looking for P of 8. We're looking at the profit based on an input of 8 hats. This one, as you probably know, you just input 8 there, so the input is 8, so the input for this H becomes an 8. And when you solve that, you get a profit of 59 based on 8 hats sold. Next question. Now it tells you he makes a profit of 98. Find the number of hats. So now the profit is known, but the number of hats is not known. Replacing back into the function, we would have this. If you remember from last time, when we were talking about the y value, in this case, we know the y value, which is the profit. This entire P of H gets replaced by the value. So the y value becomes 98, and then we can solve backwards to see how many hats lead to a profit of 98. Solving backwards, we get 11 hats. Next one. Here we have the length of a spring depends on the weight hung from it. So we're going to use L of W, the length of the spring, the dependent variable, dependent on the weight that is hung from it. So here we see a spring with a weight on it. The bigger the weight here, the more the weight, the more the string will be stretched, or the longer it will get. So here's the function for that. Again, the length depends on the weight. Use the function to answer, what is the length when the weight is 10 pounds? That one, the weight is 10, so the input value is 10, so we input 10 here for the weight, and we can solve that to get a length of 2.83. Second question, what weight hanging on the spring, or I guess what weight is hanging on the spring if the length is 4.2? Now we know the length. So this whole y, this is like the y value, that whole side of the function, L of w, gets replaced by the length here. And we can solve backwards to see what weight would create that length. Solving backwards, we can subtract 2 right here, and then multiply by 12 to get rid of that. And we have a weight of 26.4. Next one, we have a recipe states that chicken needs to be cooked for 15 minutes per kilogram of chicken and an additional 40 minutes. So 40 minutes is the minimum cooking time, and then for every 1 kilogram that the chicken weighs, you have to add 15 more minutes to the cooking time. What do you think the function for that would be? Give it a try. What does the function look like? We're going to use f of x for the cooking time, and x represents the weight of the chicken. It also asks for domain and range. We'll look at all these things. Domain, actually do try that. What would be the domain? What would be the range? Think about what are the reasonable inputs. If the inputs are x, the weight of the chicken, what are possible inputs? Could you enter a negative weight of chicken? Probably not. All right, let's take a look. So first of all, your domain is x values greater than or equal to 0. We cannot have a chicken whose weight is less than 0, so we're going to say from 0 upwards. So domain is values greater than 0. Range, basically what is the cooking time? Well, we know their minimum cooking time, it said, was 40 minutes, and then you add 15 minutes for each kilogram. So the lowest y value is 40. So our range is values of f of x that are greater than or equal to 40 minutes. And here's a function that makes sense, because we have the 40-minute cooking time. So even if x was 0, the weight of the chicken was 0 here, it would still be 40 minutes cooking time. And here, this is a linear function. It tells you that for every 1 kilogram, so let's say x is 1, this would be 15, so you add 15 minutes to cooking time. If x was 2 kilogram chicken, you'd add 30 minutes, and so on. So there's the function. Now let's use the function to answer those 2 questions. First one is, what is the weight of the chicken? Sorry, the weight of the chicken is 2 kilograms. How long to cook it? You would set it up like this. Second question, cooking time is 135 minutes. What is the chicken's weight? This one you would set up like this. The f of x part, the y part, is replaced with 135, and you solve backwards. Great. Let's take a look. Here's another one. Give this one a try. And check your work. And here we have another one. Give this one a try as well. And check your work there for that one. Now, I want you to pause this video, go to the lesson calendar, and find a video link there that is called Burning Calories. Watch this video. It will introduce basically the function that we're going to use in the next problem. So pause this video, find the link for another video on the lesson calendar, and then watch that and come back to this. So now that you've watched the Burning Calories video, you're ready to continue on your notes page. Basically, we're talking about a function that can be used to figure out how many calories you burn when you run. The dependent variable here is calories burned, because how many calories you burn depend on the time you spend running. And the function they gave in the video looks like this. So let's write that one down. Here it means calories burned dependent on time spent running. And it's important to know what units each of these variables has to be in. The time is in minutes. The weight is in pounds, which you may not be familiar with, but we'll do a conversion soon. The rate is a speed in miles per hour, and C represents the calories burned. So the goal here is going to be make a function for you specifically. So every student now is going to create a function, but that function will be unique to each student. So let's run an example now for making this function for me. So first question is, how long does it take you to run a mile? You may know your mile time. If you're a serious runner, you know what your mile time is, but you may not know. So think of it this way. If you're very, very fast, you are running a 5-minute mile. If you're kind of a medium speed runner, 9 minutes. If you're pretty slow, 13 minutes. So you decide where you lie on that spectrum there. Maybe you're even faster than that, you think, or maybe you're very, very slow, like you walk the miles. This should be even higher. But I'm just going to ask you to estimate. What do you think? What is your time for 1 mile? Okay, then you're going to convert your answer from number 1 because number 2 says, how many miles do you run in 1 hour? Here's how you would do it. So for me, this is for me specifically. I'm going to say for running 1 mile, it takes me 5.5 minutes. I'm a pretty quick runner for long distance running. So 1 mile takes me 5.5 minutes. You set that up for yours. 1 mile, you're going to use the same here, but here you'll put the time you decided on based on this first part. Then you set that equal to, we're making a proportion here, to blank some unknown number of miles for every 60 minutes, because we want a miles per hour rate. So we want to know, if I run 1 mile in 5.5 minutes, how many miles is that in 60 minutes? To solve a proportion like this, we can cross multiply, so I can do 5.5 times x and 1 times 60. So I have 5.5x equals 60. Again, for you, that'll be a different number here. And then I divide by 5.5, and I have a rate of 10.9 miles per hour. That is my rate or my speed. You should have your own unique one here. If you had a long time here, then you'll have a small number here. If you had a very quick time here, you'll have a bigger number here. Okay, now let's go to number 3. Number 3, it says, create a function using your weight and your rate. First of all, you're going to need to change kilograms to pounds because in this function we need to use pounds. So my weight is 60 kilograms. So here you will put in your weight, whatever your weight is. Multiply by 2.2. That's how you convert from kilograms to pounds. For me, that is 132 pounds. So calculate your weight in pounds. So again, this is an example for me. I have a weight of 132 and a running rate of 10.9 miles per hour. You should have unique numbers for you. Now going back to the function it gave us, we're going to replace weight here with the weight you found in pounds and your rate, your speed of running here. So for me, again, I'm going to rewrite this function. The weight has been replaced with 132 pounds. The rate has been replaced with my speed, but I've kept the t as a variable. And now if you do 10.9 squared times 132 times this decimal here, it changes my function to this. Again, everybody will have a unique function based on their weight and their rate. So everybody should have a unique function. Mine is this function. So now I have a function for calculating calories burned based on time running. And there it is. If you have a high number here, it means you're burning lots of calories. And that would be the case if you were either very heavy or very fast. Because if you're very heavy, you're carrying a lot of weight when you're running, so you burn a lot of calories. Or if you're a very fast runner, you run many miles per hour, then you can be burning more calories as well. So mine is pretty high because I'm pretty quick. Even though I don't weigh much, I'm a pretty quick runner. So I'm a pretty high multiplier here. You might have a smaller number if you're very light and slow. So let's see. Everybody should have a unique one. Now using your unique function, please answer these questions. For A, it's saying time is 25 minutes, so you put it into the calorie function and you see how many calories you burn. For B, don't forget 2 hours is actually 120 minutes, and the input here has to be in minutes, so calculate that. For C, 3.4 times 60 gives you 204 minutes, so again, 204 minutes goes into the function and it calculates how many calories you burn. And finally, look at number 5. Here, we ate too much, so we have this many calories. 1800 is a good amount, subtract those, so we're 635 over. So we need to burn those 635 calories. And now we're going to solve for the time it would take to running time to burn those calories. So in this case, the C of t value is 635. The calories is 635. So 635 replaces that part of the function, and we're going to solve this part for t. In my case, it's 19.3 minutes. I don't need to run very much to burn those calories. For you, again, if you were slow or not too heavy, this number was lower. It might take you a lot more time to burn those calories. So compare with some friends, see what happens based on your function, how much time. All right, now that you've seen that, you're ready to do some practice. There's 3 more problems provided to you. Try those with the people around you. Let's see how it goes.